What if I told you that for the entire history of human civilization, our solar system has been hiding a ninth planet in plain sight, and the only reason we did not know was that we had not yet built the right telescope to look? That telescope just opened its eyes in the Chilean Andes. The hidden world is not Nibiru. It is not Nemesis. It is not any of the fringe theories you have heard about. It is a quiet, devastating piece of mathematics from a team at Princeton, pointing at a 15-degree warp in the outer solar system that should not exist. Stay with me tonight, because what they found pulling on those orbits will change how you see the sky forever. Welcome to the Skylab. Let's get into it. Part 1. The warp that shouldn't exist. There is a region of our solar system 4 times farther from the Sun than Pluto, where the laws of physics appear to be quietly breaking down. Not breaking down in a small way. Not breaking down in a way that could be explained by measurement error or a glitchy telescope. Breaking down in a way that is, by every reasonable definition of the term, impossible. And the only honest explanation a team of researchers at Princeton has been able to come up with for what we are seeing out there is the existence of a planet. A planet nobody has ever photographed. A planet nobody has ever directly observed. A planet that, if the math is right, has been hiding in plain sight inside our own solar system for the entire history of human civilization, and we're only now, in the year 2026, coming around to the possibility that it might actually be there. This is a story about a fingerprint, a gravitational fingerprint pressed into the orbital architecture of the outer solar system, tens of billions of miles away from the warmth of the Sun. And the question we're about to spend the next 2 hours unpacking is what kind of object would have to exist in order to have left that fingerprint behind. The leading candidate, the one the simulations keep coming back to, is something that should not be possible according to current planetary formation theory. It is a rocky world somewhere between the size of Mercury and the size of Earth. It would be sitting in an orbit between 80 and 200 astronomical units from the Sun, which puts it in roughly the same neighbourhood that the Voyager 1 spacecraft is currently transmitting from. It would be cold, it would be dark, it would be silent, and it would be, if it exists, the 9th major planet of our solar system. They have given it a placeholder name. They're calling it Planet Y. Now, if you have been following outer solar system astronomy for the last decade or so, your mind has probably already jumped to a familiar place. You have probably already started thinking about Planet 9, the big one, the Neptune-class hidden world that Mike Brown and Konstantin Batygin at Caltech proposed back in 2016, the planet that was supposed to live way out at 400 to 800 astronomical units, the planet that astronomers have been hunting for almost 10 years now without success. And I want to be very clear with you right at the top of this video, Planet Y is not Planet 9. Planet Y is something different. Planet Y is closer. Planet Y is smaller. Planet Y is rocky rather than gaseous. And most importantly, Planet Y is the answer to a different anomaly. The anomaly that pointed Brown and Batygin toward a Neptune-mass world 400 AU out cannot account for the warp the Princeton team is now studying. The warp the Princeton team is studying needs something else. Something that, if we take the math at face value, is a frozen mirror of our own world, sitting in exile in the dark. So let me tell you about the warp itself, because the warp is the thing that started all of this. Out beyond Neptune, beginning at about 30 astronomical units from the Sun, there is a vast region of our solar system that most people have never thought about in any detail. It is called the Kuiper Belt. It is a graveyard of frozen rubble, ancient debris, dwarf planets, and icy bodies left over from the formation of the solar system 4.5 billion years ago. Pluto lives there. So do millions of smaller objects we are still in the process of cataloguing. By the laws of orbital dynamics, this entire region should be relatively flat, like a vinyl record spinning on a turntable. The Sun, the 8 planets, the asteroid belt, the gas giants, all of it aligns roughly with a single mathematical plane that astronomers call the invariable plane of the solar system. Everything in our cosmic neighbourhood is, more or less, lying down in that plane. But astronomers studying the deep Kuiper Belt have noticed something that the record is not supposed to do. Between roughly 80 astronomical units and 200 astronomical units from the Sun, a specific population of icy objects is not lying down. They are tilted. They are angled at about 15 degrees away from the plane of the rest of the solar system. They are swooping above and below the disk like a wobbly spinning top that has had its axis nudged. This is the warp. and the warp is the entire reason we are having this conversation. Here is why that is so unsettling. Over billions of years, the gravitational influence of the giant planets, primarily Jupiter and Neptune, should have pulled those tilted bodies back into alignment. That is what gravity does. Gravity acts as a great smoothing force in solar systems, gradually damping out wobbles and warps and irregularities, settling everything down into a steady, flat, predictable pattern. The fact that the 15-degree tilt is still there, 4.5 billion years after the solar system formed, means the warp is not a fossil. It is not a leftover from some ancient dynamical event that has just been sitting there gathering dust. It is being actively maintained. Something out there in the dark right now, in this exact moment as you are watching this video, is constantly stirring the pot. Something is keeping that 15-degree tilt alive against the relentless tendency of gravity to flatten it out. And the question that has been keeping a small group of astronomers at Princeton awake at night for the last several years is the most obvious question you could ask. What is doing the stirring? Stay with me, because the answer they have come back with is going to challenge every assumption you have about the solar system you grew up learning about in school. We were all taught there are 8 planets, 9 if you count Pluto, and that the textbook is more or less complete. The Princeton claim, if it survives the test that is about to be run on it, says we missed one, and it is sitting closer than anyone ever thought a hidden world could possibly be. Part 2. The Frozen Graveyard and the Flat Record. To understand why the warp matters, you have to first understand the place where the warp lives, because the Kuiper Belt is not just some random region of empty space out past Neptune. It is one of the most important and least appreciated structures in the entire solar system. It is the museum. It is the archive. It is the place where the leftover ingredients of planetary formation were swept up and parked 4.5 billion years ago, and it has been sitting there, more or less undisturbed, ever since. If you want to understand how our solar system was built, you do not look at the Earth. The Earth is too geologically active. Plate tectonics has scrubbed away almost all of the original surface. You do not look at Mars. Mars is too eroded. You look at the Kuiper Belt. Because the Kuiper Belt is where the original ingredients are still mostly in their original packaging. The belt begins at roughly 30 astronomical units from the Sun, which puts its inner edge at about the orbit of Neptune. From there it stretches outward to somewhere around 50 AU, where the so-called scattered disk takes over. Beyond that lies the inner Oort cloud, then the outer Oort cloud, and then eventually the boundary of the Sun's gravitational influence. The Kuiper Belt itself is enormous. It is hundreds of times wider than the asteroid belt that sits between Mars and Jupiter. It is also dramatically colder. The temperature out there is somewhere around 40 to 50 Kelvin, which is roughly negative 400 degrees Fahrenheit, cold enough to freeze nitrogen and methane, and just about every other gas you can name into solid ice. The bodies that live in the Kuiper Belt are mostly mixtures of water ice, methane ice, ammonia ice, and rocky cores. They are dim, they are slow, and they are hard to see. For most of the 20th century, we knew almost nothing about this region. The first Kuiper Belt object after Pluto was not discovered until 1992 by astronomers David Jewett and Jane Liu working in Hawaii. Since then, the cataloguing effort has expanded enormously, and we now have orbital data on something like 3,000 confirmed Kuiper Belt objects, with tens of thousands more believed to exist below our current detection threshold. But 3,000 is still a tiny fraction of what is actually out there. Estimates of the total population of Kuiper Belt objects larger than about 100 kilometers across run into the hundreds of thousands. The total mass of the belt, if you added up all the icy debris, is somewhere between 5 and 10% of the mass of the Earth. Not very much, by planetary standards, but spread out over an enormous volume, with billions of individual objects, each one carrying its own little orbital story. Now here is the key thing about the Kuiper Belt that makes it useful as a diagnostic tool. The orbits of all those bodies, taken collectively, encode the gravitational history of the outer solar system. Every body out there is following a trajectory determined by the combined pull of the Sun and the giant planets and any other massive object in the neighbourhood. If you map enough of those orbits, you start to see patterns, you start to see populations, you start to see structure that tells you something about what has been pushing on those bodies over the 4.5 billion years of solar system history. And one of the most striking things you should see, if our model of the solar system is correct, is that the orbits of the Kuiper belt should be nearly flat. They should mostly lie in the invariable plane, just like everything else. There should be a thin disk of icy debris rotating around the Sun in roughly the same direction and at roughly the same orientation as the planets. Most of the Kuiper belt does behave that way. The classical population, the bodies that sit in roughly circular orbits in the inner part of the belt, are all aligned within a few degrees of the invariable plane. That is what theory predicts, and that is what we observe. The system has done what gravity is supposed to do. It has settled, it has flattened, it has parked the leftover material in a thin disk. This is unremarkable. This is what we expected. But then you start looking at the bodies that orbit further out. You start looking at the population that lives between 80 and 200 astronomical units from the Sun, in a region that is sometimes called the detached disk, or the inner Oort cloud transition zone. And you find something different. The orbits of these bodies are not flat, the orbits of these bodies are tilted. Specifically, they carry a collective inclination of about 15 degrees relative to the invariable plane. They are angled. They swoop above and below the disk in a coherent, organized way, as if something has been gently pushing on them, lifting one side and depressing the other for billions of years. 15 degrees may not sound like much. If you tilted a vinyl record on its turntable by 15 degrees, it would still look roughly flat to a casual observer. But for the outer solar system, 15 degrees is enormous. It is far outside the range that random orbital evolution can explain. It is far outside the range that any known dynamical mechanism in our current model of the solar system can produce. And, critically, it is far outside the range that should still exist after 4.5 billion years of gravitational flattening from Jupiter and Neptune. Whatever produced that 15-degree tilt, it should have been damped out long ago. The fact that we are still seeing it today, in our current observational data, means something is still actively producing it. Something is still actively maintaining it. So the Princeton team, like several other research groups around the world over the past few years, started asking the question, what kind of object, in what kind of orbit, would be capable of sustaining a 15-degree warp in this specific population of trans-Neptunian bodies against the relentless smoothing pressure of the rest of the solar system over the entire history of the solar system? What gravitational signature would have to be present to leave this exact fingerprint? And this is where things get interesting, because the first answer that comes to mind is the one that has been on the table for almost 10 years. The first answer that comes to mind is Planet 9. But as we're about to see, Planet 9 cannot be the answer. The math does not work. The geometry is wrong. Planet 9 is too far away, in the wrong place, with the wrong gravitational influence to produce the warp we are seeing. Whatever is causing the 15-degree tilt has to be something else, something we have not yet considered, something closer. Part 3. The 15-degree tilt in detail. Let me walk you through what the data actually looks like, because the precision of the measurement is part of what makes this story so unsettling. We're not talking about a vague or fuzzy result. We are talking about a clean, statistically significant signature in a population of carefully tracked celestial bodies. The astronomers studying the warp have been at this for years. They have used wide-field optical surveys from observatories on the ground in Hawaii, in Chile, and at Cerro Tololo. They have used data from space-based platforms. They have cross-referenced multiple independent catalogues of trans-Neptunian objects to make sure no single survey is biasing the result. And the answer keeps coming back the same. The bodies between 80 and 200 astronomical units have orbits that are systematically tilted 15 degrees away from the rest of the solar system, and the pattern is too coherent and too persistent to be a statistical fluke. What does that actually mean in practice? Picture the solar system as a giant flat plate, with the Sun at the centre and all the planets orbiting around it in roughly the same horizontal plane. Now picture, way out past the orbit of Neptune, a second, smaller plate. This second plate is not lying flat. It is tilted. It is rotated about 15 degrees off from the main plate, and the bodies that live on this second tilted plate are following its tilted orientation, not the main one. They are not crossing through the main plane at random angles. They're not scattered. They're organised. They're all riding the same tilted disk like icy passengers on a slightly cocked merry-go-round. This kind of organised warp is, in dynamical terms, what we call a coherent inclination signal, and coherent inclination signals are extremely hard to produce by chance. The natural state of a population of orbiting bodies after a few billion years of gravitational interaction is randomness. Orbits decay, inclinations average out, asymmetries get smoothed away. To still see a coherent 15-degree warp today, when the same physics that produced our flat solar system has had 4.5 billion years to flatten everything else, requires an active source of disturbance. Something has to be doing work. Something has to be continuously injecting tilt into that population. Otherwise the warp would have damped out hundreds of millions of years ago, and we would be looking at a flat disk like everywhere else. Now, dynamicists have considered a number of possible explanations for what could be sustaining the warp. One possibility is that the entire outer solar system has been tilted by a long-past stellar flyby. There is some evidence that other stars have passed close enough to our Sun in the deep past to gravitationally disturb the outer disk. If a passing star pulled on the outer Kuiper belt at just the right angle, it could have imparted an initial inclination to the 80 to 200 AU population, and depending on the dynamics, some of that inclination might still persist today. This is one of the null hypotheses we have to keep on the table. It is possible that the warp is a fossil from a past event rather than a sign of an active perturber. Another possibility is that the warp is produced by an unmodelled distribution of small bodies. If there are enough small icy objects out there that we have not yet detected, and if their collective gravitational pull is structured in just the right way, they might in principle sustain the warp without any single large body being responsible. This is harder to make work mathematically, because you need a lot of mass distributed in a very specific configuration, but it is also a hypothesis the field has to take seriously. A third possibility, and this is the one the Princeton team has been investigating, is that there is a single discrete object out there, embedded in the warp itself, whose gravity is strong enough to keep its neighbours locked in their tilted orbits. This is the Planet Y hypothesis, and the reason it is currently the leading explanation is that when you run the simulations, a single embedded body produces a warp signature that matches the observed data more cleanly than any of the alternative explanations. The geometry of the tilt, the distribution of orbital elements among the affected bodies, the specific way the warp varies with distance from the Sun, all of it fits more naturally if there is one massive object stirring the pot from inside the warp than if you try to explain it with a flyby fossil or a diffuse mass distribution. I want to be careful here, because this is the kind of place where pop science coverage tends to overshoot. The Princeton result is a strong inference. It is not a direct observation. The team has not photographed Planet Y. The team has not measured the gravitational pull of Planet Y in any direct way. What the team has done is run a series of computer simulations of the outer solar system, varying the assumed mass and orbit of a hypothetical perturbing body, and asking the simulations which combination of mass and orbit produces the best match to the observed warp. The answer that comes back, the cleanest fit, is a body of Mercury to Earth mass, orbiting somewhere in the 80 to 200 AU range, on a moderately tilted orbit that places it inside the warp it is producing. That is the case. That is the entire case. The question of whether Planet Y actually exists comes down to whether anyone can independently verify it, either by replicating the simulation with different starting assumptions, or, much more importantly, by pointing a telescope at the right patch of sky and finding something moving there. Which brings us to the obvious next question. If the inference from the warp is so strong, why has nobody just gone out and looked? Why has nobody pointed a telescope at the right region of sky and confirmed the existence of this hidden world? The answer to that question is going to take us through some of the most beautiful and frustrating physics in modern astronomy. But before we get there, I want to back up. Because the method we are using here, the method of inferring an unseen planet from anomalies in the orbits of seen objects, is not new. It has a history. And the history is one of the great success stories of all of science. It is the story of how we found Neptune. So let me take you back to the late 1700s, to an English astronomer named William Herschel, scanning the sky from his garden in Bath with a telescope he had built himself. Part 4, Herschel, Uranus, and the Wobble that broke Newton. The year was 1781. The American Revolution was still in progress. The French Revolution was still 8 years away. And in the sleepy English town of Bath, a German-born musician named William Herschel was spending his evenings doing something almost nobody else in the world was doing. He was building telescopes, not just buying them. building them, grinding the mirrors himself, polishing them by hand, mounting them in homemade frames in his garden. Herschel had become obsessed with astronomy in his 30s, and he had taught himself, mostly through textbooks and trial and error, how to construct optical instruments more powerful than anything commercially available at the time. He was a serious amateur in the old sense of that word, before it became a polite way of saying not a professional. He was an amateur because he did it for love. On the night of March 13th, 1781, Herschel was doing what he often did. He was sweeping the sky with one of his homemade telescopes, looking for double stars, looking for nebulae, looking for anything interesting. His goal that night was probably just to add to his ongoing star catalogue. He was not looking for a planet. Nobody in the year 1781 expected to find a planet. The planets had all been known since antiquity: Mercury, Venus, Mars, Jupiter, Saturn. These were the wandering stars the ancients had named, and they were the only worlds anyone thought existed. The idea that there might be more planets, hidden out beyond Saturn, was simply not on the menu of things educated astronomers expected to discover. But on that March night, as Herschel swept his telescope through the constellation of Gemini, he noticed something odd. There was a small disc-shaped object that did not behave like a star. Stars appear as points of light, no matter how powerful the telescope. This object showed a measurable disc. It was clearly an object, not a point. Herschel initially assumed it was a comet, because comets are the other kind of solar system object that sometimes appears as a fuzzy disk. He reported it as a comet. He sent letters about it to other astronomers, but over the following weeks, as more astronomers tracked the new object, something began to become clear. It was not behaving like a comet at all. Comets follow elongated, eccentric orbits that bring them close to the Sun and then fling them back out. This object was moving slowly, steadily, and on what appeared to be a roughly circular orbit far beyond Saturn. By the time the math got worked out several months later, the conclusion was inescapable. Herschel had not discovered a comet. He had discovered a planet, the first new planet in the recorded history of human astronomy. It was twice as far from the Sun as Saturn, which had been the outermost known planet for thousands of years. It was bluish-green in colour, dimly visible to the naked eye under good conditions, and from that point forward, every textbook in the world had to be revised. There were now 7 planets. Then, after some debate about names, the new world was christened Uranus, after the Greek god of the sky. Now here is where the story turns, and where it becomes relevant to Planet Y. For several decades after Herschel's discovery, astronomers tracked Uranus carefully. They calculated its orbit, they predicted where it should be at any given time, and they noticed, to their growing puzzlement, that Uranus did not always show up where it was supposed to. The orbit had a wobble. It was a small wobble, just a tiny deviation from where Newton's laws of gravity said the planet should be. But it was real, and it was reproducible, and over the years it became increasingly hard to ignore. Some astronomers proposed that Uranus simply had a slightly different orbit than originally calculated. Others suggested that perhaps Newton's law of gravity was not quite right at such enormous distances, that perhaps we needed to modify the inverse square law or add some correction term to make the orbit work out. This was a serious scientific position in the 1830s. There were respectable physicists who genuinely believed that the discovery of Uranus had revealed a flaw in Newtonian mechanics that needed to be patched. But there was a third possibility, and it was the one a small number of mathematicians and astronomers began to take seriously in the 1840s. The third possibility was that there was another planet, even further out than Uranus, whose gravitational pull was tugging on Uranus and producing the wobble. If you could just figure out where that hidden planet was and how massive it had to be, you could explain the entire wobble without having to throw out any of Newton's laws. The wobble would not be a problem with the physics. It would be evidence of something we had not yet seen. The man who finally cracked the math, with pencil and paper and patience and an enormous amount of computational labour, was a French mathematician named Urbain Le Verrier. He was working at the Paris Observatory in the 1840s, and he took on the Uranus problem as a personal mission. He would spend years grinding through the equations, calculating the orbit Uranus actually had, the orbit Uranus should have if there was nothing else out there, and the difference between the two. The difference, he reasoned, had to be caused by the gravitational pull of an unseen body. And from the size and direction of that difference, he could in principle work out where the unseen body had to be. He could solve for an entire planet using nothing but mathematics. The story of what happened next is, even today, almost 2 centuries later, one of the most remarkable triumphs in the history of science. And it is also, I want to emphasize, the exact same intellectual maneuver the Princeton team is now performing with the warp in the Kuiper Belt. They are doing what Leverrier did. They are taking the anomalous behavior of seen objects and using it to predict the location of an unseen one. The method is identical. The only difference is the data. So let me tell you what Leverrier did and what happened when astronomers actually looked. Part 5. Leverrier and the discovery of Neptune. By the summer of 1846, Urbain Leverrier had finished his calculations. He had worked through the residuals in the orbit of Uranus, the small but persistent deviations between observed position and predicted position, and he had derived from those residuals a complete prediction. He had calculated the mass that the unseen perturbing planet would have to have. He had calculated the orbital distance it would have to be at, and he had calculated where in the sky, on a given date, an astronomer should point a telescope in order to see it. The prediction was specific. It was not vague. It was a precise location, given in coordinates of right ascension and declination, with an estimate of how big the disk should appear and how bright it should look through a moderately large telescope. Leverrier sent his prediction to several major observatories in Europe, asking them to check his work by actually observing the predicted location. Most of the observatories he wrote to were uninterested. The idea that you could just calculate where a planet had to be and then go find it sounded to most working astronomers in 1846 faintly absurd. Astronomy was, in the prevailing view of the time, a discipline of patient cataloguing. You looked through telescopes and you wrote down what you saw. You did not predict celestial bodies into existence with arithmetic. The notion that mathematics could conjure a planet out of pure inference was, to many astronomers, beneath the dignity of the profession. And so Leverrier's letters mostly went unanswered. Mostly, but not entirely. One of the letters reached an astronomer named Johann Galle at the Berlin Observatory. Galle was a younger man, less burdened by the conservatism of his elders, and he was intrigued by Leverrier's prediction. He decided to give it one night. Just one. He would point the Berlin Observatory's telescope at the location Leverrier had specified and see if anything was there. He recruited a graduate student named Heinrich Darès to help him. They worked through the night of September the 23rd, 1846. Galle would call out the positions and brightnesses of stars he could see through the eyepiece. Darès would check the positions against a recently published star chart. They were looking for one specific thing. They were looking for an object that appeared in the eyepiece but was not on the chart. An object that should not be there, because no star catalogue had ever listed it, but that would be there if Leverrier was right. It took them less than an hour. Galle called out a position. Darès checked the chart. The chart was blank in that location. Galle looked again. The object was small, just a faint disk, dim and bluish. But it was there. It was exactly where Leverrier had said it would be. The discrepancy from prediction was less than 1 degree. By the standards of modern astronomy, that is a slightly imprecise result. By the standards of pencil and paper celestial mechanics done in the 1840s, it was uncanny. Leverrier had calculated the position of an unknown planet, and Galle had pointed his telescope at the calculated position, and the planet had been there. The new world was named Neptune, after the Roman god of the sea. It was the 8th planet in our solar system, and more importantly than that, it was the first major planet discovered not by direct observation, but by mathematical inference. Leverrier had, in a very real sense, found Neptune in his head before any human eye had ever seen it. The telescope had merely confirmed what the mathematics had already established. This moment, September 23rd, 1846, is one of the founding moments of modern astrophysics. It is the moment that established a method, a way of doing science, that would shape outer solar system astronomy for the next 2 centuries and counting. The method is this. You catalogue the orbits of the bodies you can see. You compare those orbits to what your physics predicts they should be. If you find a discrepancy that is too large to be measurement error and too persistent to be a statistical fluctuation, you ask what unseen mass would have to exist in order to explain the discrepancy. You solve for the perturbing body, and then, having solved for it, You point a telescope at the predicted location to see if you can find it directly. If you do, you have discovered a new world. If you do not, you go back and check whether your physics is actually right. This is exactly the method the Princeton team is using right now in 2026 on the warp in the Kuiper belt. The bodies they can see, the trans-Neptunian objects in the 80 to 200 AU range, are doing something their physics does not predict. The 15-degree tilt is the discrepancy. The Princeton team has solved for what unseen body would have to exist in order to produce that tilt, and the answer they have come back with is Planet Y. The next step, the step that has defined this method since 1846, is to point a telescope at the right region of sky and see if Planet Y is actually there. That is the test. That is what the Vera Rubin Observatory is about to begin doing. But before we get there, I have to tell you about the other major attempt to use the Leverrier method on the outer solar system in the modern era. Because this attempt is the immediate scientific predecessor of the Planet Y claim, and it is the reason that any conversation about hidden worlds in the outer solar system has to start with the same question. Are we sure we have not already been here before? Are we sure this is not just Planet 9 in a new costume? That brings us to 2016, to Pasadena, California, to Mike Brown and Konstantin Batygin at Caltech, and to the planet that has eluded astronomers for almost a decade now. Part 6. Brown, Batygin, and Planet 9. In January of 2016, 2 Caltech astronomers published a paper in the Astronomical Journal that set off the most intense outer solar system planet hunt in modern history. The astronomers were Mike Brown, who had previously become famous, or in some quarters infamous, for being the man whose research led to Pluto being demoted from planetary status in 2006, and Konstantin Batygin, a younger theoretical astrophysicist who specialized in the dynamics of planetary systems. The two of them had been studying a peculiar set of trans-Neptunian objects, a small population of extremely distant bodies known as extreme TNOs, whose orbits had begun to look suspiciously organized. The objects in question were a half dozen or so bodies in the outer solar system whose orbits had perihelion distances, the closest points to the Sun, that were unusually clustered together in space. Normally, you would expect the perihelion points of randomly evolving distant orbits to be scattered evenly around the Sun. There is no reason for them to all point in the same direction. But the extreme TNOs Brown and Batygin were studying did all point in roughly the same direction. Their perihelion arguments, which is the technical term for the angle that defines where in the sky the orbit's closest approach to the Sun occurs, were all clustered within a narrow range. The probability of this happening by chance, the two astronomers calculated, was vanishingly small. Something was producing the clustering. Brown and Batygin proposed that the something was a hidden planet, a massive, distant, undiscovered world whose gravitational pull was acting as a kind of orbital shepherd, keeping the perihelion points of the extreme TNOs aligned. They did the math. They estimated the planet's mass at somewhere between 5 and 10 Earth masses, putting it firmly in the Neptune-class category, an ice giant rather than a rocky terrestrial world. They estimated its orbital distance at somewhere between 400 and 800 astronomical units from the Sun, vastly farther out than anything humans had ever imaged. They estimated its orbital period at somewhere between 10 and 20,000 years, and they gave it a name. They called it Planet 9. The Planet 9 paper, published in 2016, set off an enormous wave of excitement in the planetary science community. It was the first serious quantitative argument for an additional major planet in our solar system since the early 1900s. It was the modern continuation of the Leverrier method, applied to a new set of orbital anomalies in a region of space we had only recently begun to map, and it triggered an immediate planet hunt. Telescopes around the world began scanning the sky, looking for the small, dim, slow-moving point of light that Planet 9 should appear as. Astronomers volunteered their observing time. Citizen science projects were set up to crowdsource the search through public computing resources. The expectation, in the early excitement of 2016 and 2017, was that Planet 9 would be found within a few years. A decade later, in 2026, Planet 9 has not been found. The hunt continues, but the hunt has become quieter. Several major surveys have been completed, several large regions of sky have been thoroughly searched, and Planet 9, if it exists, has stubbornly refused to show itself. There are several possible reasons for this. Maybe the orbital parameters Brown and Batygin estimated are slightly off, and the planet is in a part of the sky we have not yet adequately searched. Maybe the planet is much darker, and therefore much fainter than expected, and our current surveys are not sensitive enough to pick it up. Maybe the planet has an unusually long orbital period and is currently near aphelion, the farthest point from the Sun, where it would be at its faintest and most spread out across the sky. All of these are reasonable explanations for why a real planet might still be eluding detection. But there is also a less comfortable possibility, and this possibility has been gaining traction in the planetary science community over the past few years. The less comfortable possibility is that Planet 9 does not exist. The orbital clustering Brown and Bettigen observed in 2016 may have been at least partly a product of observational selection effects rather than a real signal. As more trans-Neptunian objects have been discovered and added to the catalogue over the past decade, the original clustering signal has weakened somewhat. Some, though not all, of the apparent organisation of those extreme TNO orbits can be explained by the fact that we are more likely to discover objects whose orbits bring them close to the Sun than objects whose orbits keep them perpetually distant. When you correct for that bias, the case for a single discrete perturber gets weaker. This does not mean Planet 9 has been ruled out. The Brown-Bettigen analysis is still on the table, and there are still enough outer solar system anomalies that an additional Neptune-class planet remains a serious possibility. But the certainty has eroded. The scientific community has learned to be more cautious about claims of inferred planets and to demand a higher bar of evidence before treating an inferential argument as established science. This caution is healthy. It is also exactly the kind of caution that any new claim, including the Planet Y claim, is going to have to meet. Now, here is the critical fact about Planet 9 that matters for our story today. The Planet 9 hypothesis is about a body at 400 to 800 astronomical units on a long, eccentric, highly inclined orbit with a Neptune-class mass. The math for Planet 9 specifically does not predict, and cannot account for, the 15-degree warp that the Princeton team is studying. Planet 9 is too far away. Planet 9 is in the wrong orbit. The gravitational resonance Planet 9 would set up in the inner Kuiper belt is not the kind of resonance that would produce the warp signature we are seeing. To put it bluntly, even if Planet 9 exists exactly as Brown and Bettigen originally proposed, it cannot be the cause of the 80 to 200 AU tilt. So if Planet 9 cannot be the answer, what is? What kind of object, in what kind of orbit, would actually produce the warp we are seeing? This is the question Princeton has been working on, and the answer they have come back with is something that is, in its own way, even more startling than Planet 9. Because Planet 9, if it exists, fits relatively neatly into our existing model of the solar system. A Neptune-class body at 400 AU is unusual but not impossible. A Mercury-to-Earth mass rocky world at 150 AU is something else entirely. It is a body that, by the rules of planet formation as we currently understand them, should not be there at all. Part 7. Why Planet 9 cannot be the answer. I want to take a moment to spell out in concrete terms why the Princeton team had to rule out Planet 9 before they could propose Planet Y. Because if you do not understand why Planet 9 fails to explain the warp, you might assume that Planet Y is just a variant of Planet 9. It is not. They are fundamentally different hypotheses, and the geometry of why they are different is worth understanding. Planet 9, in the Brown-Bettigen framework, is theorized to live somewhere between 400 and 800 astronomical units from the Sun. Let me put that distance in perspective for you. The Voyager 1 spacecraft, launched by NASA in 1977, has been flying away from the Sun for almost half a century at a speed of roughly 17 kilometers per second. That works out to about 3.5 AU per year. After 49 years of continuous outbound travel, Voyager 1 is currently transmitting back from approximately 165 astronomical units. Light from the Sun takes about 23 hours, almost a full Earth day, to reach Voyager 1 at its current distance. To put it another way, Voyager 1 has been moving outward continuously for half a century, and it is still inside the inner edge of the Planet Y candidate region. To reach the inner edge of the Planet 9 candidate region at 400 AU, Voyager 1 would need to keep travelling for another 70 years. To reach the outer edge at 800 AU, more than 150 years. That is the scale we're talking about. Planet 9, if it exists, is mind-bogglingly far away. It is so far that the gravitational pull it exerts on bodies in the inner Kuiper belt is incredibly weak. Yes, gravity is a long-range force. Yes, gravity falls off as the inverse square of distance. which means it never quite reaches zero. But the gravitational influence of a 5 Earth mass body at 500 AU on a population of objects at 150 AU is, in absolute terms, tiny. It is enough to slowly herd the perihelion points of extreme orbits over hundreds of millions of years, which is what Brown and Batygin originally proposed it was doing. But it is not enough to actively maintain a 15-degree inclination warp in a closer-in population of bodies. The geometry simply does not work. There is a more technical reason as well that has to do with the way orbital resonances function in the outer solar system. Resonances are stable orbital relationships in which one body's orbit is locked into a fixed ratio with another body's orbit. Pluto, for instance, is in a 3-to-2 resonance with Neptune, meaning Pluto completes 2 orbits for every 3 orbits Neptune completes. Resonances are powerful gravitational anchors, and they can sustain orbital structures over very long timescales. But the resonances Planet 9 would set up in the Kuiper belt are the wrong kind to produce the observed warp. They would tend to align orbits in eccentricity rather than in inclination. They would tend to organize the perihelion points of extreme TNOs, which is exactly the original Planet 9 signature, rather than tilt a population of moderate distance bodies up out of the plane. What would it take to actually produce the warp? You need a body whose orbit is itself inclined relative to the invariable plane, sitting close enough to the affected population to exert a significant tilting torque on them, and massive enough to maintain that torque against the smoothing pressure of the rest of the system. The simulations the Princeton team has run are essentially a search through the parameter space of possible perturbing bodies, asking which combination of mass, distance, and orbital inclination produces a warp signature that matches the observations. The answer that comes out of those simulations is consistent. It is not a Neptune-class ice giant at 500 AU. It is a smaller body, much smaller, sitting much closer in. Specifically, it is a body in the mass range from Mercury to Earth, in an orbit between 80 and 200 AU, with a moderate inclination of its own that places it inside the warp it is producing. This is a body that, if it exists, is dynamically embedded in the population it is shepherding. It is not pulling the warp from outside, it is sitting in the middle of the warp and stirring it from within. This is a fundamentally different kind of object than Planet 9. Planet 9, if it exists, is a distant gas giant on a lonely outer orbit. Planet Y, if it exists, is a rocky terrestrial world embedded in the trans-Neptunian population. Planet 9 is exotic in its remoteness. Planet Y is exotic in its proximity. And, as we are about to see, Planet Y is exotic in another, much deeper way as well. Because the very existence of a rocky Earth-class world at 150 astronomical units from the Sun should not be possible according to our current theory of how planets form. This is the part of the story where physics starts to creak. Because if the Princeton team is right, and there really is a frozen Earth out there in the dark, then we have to figure out how it got there. And the answer, no matter which way you turn it, is going to require us to revise something fundamental about our model of the early solar system. Part 8. The Princeton simulations and the case for Planet Y. So let me walk you through what the Princeton team actually did, because the case they have built for Planet Y is not based on a single elegant equation. It is based on thousands of computer simulations of the outer solar system, each one a slightly different scenario, each one tested against the observed data on the warp. This is brute force theoretical astrophysics. It is the modern equivalent of what Leverrier did with pencil and paper, except the modern version uses massive supercomputers and runs millions of orbital integrations to test every plausible combination of perturbing parameters. The conclusion the simulations converge on is what gives the Planet Y hypothesis its empirical weight. The setup is straightforward in concept, though enormously complex in execution. You take the current observed positions and orbital elements of all the trans-Neptunian objects whose orbits define the warp. You then build a computational model of the solar system, including the Sun, the 8 known planets, and a hypothetical perturbing body whose mass, orbit, and inclination you can vary. You let the simulation run forward or backward, in time over millions or billions of years, watching how the orbits of the test bodies evolve under the combined gravitational influence of all the modelled bodies including the hypothetical perturber, and then you compare the resulting evolved orbits to what we actually observe today. If the simulation produces a warp that matches the observed warp, you have found a candidate perturber. If it does not, you adjust the parameters and try again. The Princeton team did this exhaustively. They tested perturbing bodies at every plausible mass, from the mass of Pluto on the low end up to several Earth masses on the high end. They tested every plausible orbital distance, from the inner edge of the Kuiper belt out to the outer edge of the candidate Planet 9 region. They tested a wide range of orbital inclinations and eccentricities, and what they found is that the parameter space is highly constrained. Not every perturbing body produces a warp that matches the data. Most do not. The ones that do form a tight cluster in parameter space, and the cluster centers on a body in the Mercury to Earth mass range, on a relatively low eccentricity orbit between 80 and 200 AU, with a moderate inclination of its own. This is why the Princeton claim has empirical traction. It is not that the team randomly proposed Planet Y and then asserted it could explain the warp. It is that the team systematically searched for any body that could explain the warp, and the search came back with a narrowly constrained answer. Within the limits of the simulation methodology, the only kind of body that fits is a rocky terrestrial world embedded in the warp it produces. Other answers do not work. A more massive body would overwarp the population, producing inclinations larger than 15 degrees. A less massive body would fail to maintain the warp against gravitational smoothing. A body in a different orbit would produce the warp at a different distance from the Sun. The fit is, within the constraints of the analysis, unique. Now, I want to flag the obvious caveats here, because pop science coverage of inferential planet claims tends to skip past them. The Princeton simulations are only as good as the inputs. If the observed data on the trans-Neptunian objects is biased by selection effects, that is, if our catalogue of these objects systematically overrepresents bodies whose orbits make them easier to detect, then the apparent warp could be partly artifactual, and the inferred perturber could be a phantom. The same critique that has weakened the case for Planet 9 over the past decade applies here too. We have to be careful. We have to ask whether the warp we are measuring is real, or whether some part of it is an observational illusion. The Princeton team has, in their published work, attempted to control for these effects, but no analysis is perfect, and the field will have to independently verify their conclusions before the case for Planet Y can be considered established. Furthermore, the simulations themselves rest on assumptions about the gravitational physics of the outer solar system that are well tested, but not infallible. The model assumes Newtonian gravity is exactly correct out to distances of 200 AU or more, which it almost certainly is. But if there are any subtle modifications to gravity at extreme distances, those modifications would change the outcome. The model also assumes that the population of trans-Neptunian objects has not been perturbed by recent events we have failed to account for, such as a close passage of another star within the last few 100 million years. Stellar flybys are not common, but they are not impossible, and one in the right place at the right time could mimic the gravitational signature of a perturbing planet without any planet actually existing. These are the alternative explanations that the field will have to systematically eliminate before the Planet Y hypothesis can graduate from inference to established discovery. That said, even with the caveats fully accounted for, the Princeton case is the leading explanation for the warp. Other research groups have run their own simulations with somewhat different methodologies and have come to broadly similar conclusions. The convergence of multiple independent analyses on a body in roughly the same mass and distance range as Planet Y is a strong sign that the result is robust. It is not yet proof. But it is a strong scientific argument, and the strength of the argument is what justifies the next step. The next step is the search. So let me now tell you what kind of object you would actually be looking for if you were trying to find Planet Y. Because the surface conditions, the appearance, the physical reality of this hypothetical world are unlike anything else we have ever directly observed. To stand on the surface of Planet Y would be to stand somewhere that genuinely qualifies as the edge of human imagination. Part 9. What kind of world Planet Y would actually be? Let me ask you to do something. Close your eyes for a moment, just briefly, and imagine yourself standing on the surface of Planet Y. Imagine you have somehow been transported through some impossible sci-fi mechanism to the day side of this world. The first thing you would notice is the silence, not the metaphorical silence of being alone, the literal physical silence of being in a place where there is no atmosphere to carry sound. Planet Y, by every reasonable model of its environment, has no atmosphere as we understand the word. Whatever gas it might once have held when it formed has long since condensed and frozen onto the surface as a thin layer of ice. There is no air. There is no wind, there is no weather, there is nothing for sound waves to propagate through. If you struck a rock with a hammer, the hammer would make no noise. The rock would just split in absolute silence. The second thing you would notice is the cold. The temperature on the surface of planet Y, given its distance from the Sun, is somewhere in the neighbourhood of 20 to 30 Kelvin. That is roughly negative 420 degrees Fahrenheit. It is cold enough to freeze nitrogen solid. It is cold enough to freeze methane solid. It is so cold that the chemistry of life as we know it cannot function. Liquid water cannot exist. Organic chemistry slows to a crawl. You would not freeze to death on the surface of planet Y in the way you would freeze to death in Antarctica. You would freeze instantaneously. The surface would extract heat from your body so rapidly that the boundary between living tissue and frozen mineral would resolve in seconds. The third thing you would notice is the darkness. At a distance of 150 astronomical units from the Sun itself is no longer the life-giving disk we know from Earth. The Sun is reduced to the brightest star in a black sky. It is too distant to warm anything. It is too faint to cast a meaningful shadow. The sunlight reaching the surface of planet Y is on the order of 1/20,000th of what reaches Earth, depending on the exact distance. There is no day and night cycle in any meaningful sense. There is only a permanent dim starlight, slightly brighter when the rotation of the planet brings the Sun above the horizon, slightly dimmer when it sets. It is not a place that has weather, or seasons, or sunrises in any way you would recognize. It is a place of perpetual cosmic twilight. The fourth thing you would notice, if you could survive long enough to notice anything, is that the surface itself is dark. This is one of the most important physical features of planet Y from the standpoint of trying to find it. The bodies in the outer solar system tend to be covered in dark, carbon-rich material, processed over billions of years by exposure to cosmic radiation. The surfaces of distant Kuiper Belt objects are often as dark as fresh asphalt, with reflectivity, what astronomers call albedo, of just a few percent. If planet Y has a surface like that, it would absorb almost all of the meager sunlight that reaches it. What little light it does receive, it would barely reflect. From any practical observational standpoint, planet Y would be one of the darkest objects in the solar system, intrinsically and structurally hard to see. But here is the part that should make your hair stand on end. Despite all of this, despite the darkness and the silence and the cold, planet Y is massive enough to gravitationally herd the icy debris around it into a coherent 15-degree warp that we can measure from Earth, 4 billion miles away. That is the strange thing, the contradiction at the center of this whole story. A world too dark to see, too cold to live on, too far away to visit, is somehow making its presence known through gravity alone. It cannot hide. The math gives it away. Every icy body in the 80 to 200 AU zone is in a sense gossiping about the existence of planet Y. They are telling on it. Every tilted orbit out there is a little gravitational note left behind, like the smear of a fingerprint on glass saying, somebody was here, somebody is still here. And the question of who that somebody is, the question of how this frozen rocky world ended up parked 150 astronomical units from the Sun has two competing answers. Both of them would, if confirmed, rewrite a chapter of the history of our own solar system. The first answer is that planet Y was born here, born close to home, alongside the Earth and Venus and Mars, and then violently exiled into the dark. The second answer is that planet Y was not born here at all, that it is a wanderer, a captured rogue, a planet that drifted in from interstellar space and was caught in the Sun's gravitational web in some long-forgotten encounter. We cannot yet tell which one of these is true, but both of them are stranger and more profound than anything we have ever previously had to consider for a body in our own solar system. Let me tell you about the lost sibling first. Part 10. The lost sibling scenario. The first hypothesis for how planet Y got to where it is goes back to the chaotic first 100 million years of our solar system. To understand it, you have to understand something about how planet formation actually happened. Because the textbook story you learned in school, the orderly story of dust grains coalescing into planets in their final orbits, is wrong. Or rather, it is a simplified version of a much messier reality. The actual early solar system was a violent and dynamic place, and the planets we have today are the survivors of a process that included an enormous amount of orbital migration, gravitational scattering, and outright catastrophe. Here is what we now think happened. About 4.5 billion years ago, the Sun was newly formed, surrounded by a flat rotating disk of gas and dust that astronomers call the protoplanetary disk. Within this disk, dust grains slowly coalesced into pebbles, pebbles into boulders, boulders into kilometre-scale planetesimals, and planetesimals into protoplanets. In the inner part of the disk, where temperatures were high enough that water ice could not condense, the protoplanets that formed were rocky. These would become the terrestrial planets. In the outer part of the disk, beyond what astronomers call the snow line, water and other ices were stable, and the protoplanets that formed could accumulate enormous icy envelopes. These became the gas giants and ice giants. But the early solar system was not a static place. The giant planets, in particular, did not stay in the orbits where they originally formed. Modern dynamical simulations strongly suggest that Jupiter, Saturn, Uranus, and Neptune all underwent significant orbital migration during the first few 100 million years. Jupiter probably formed somewhere closer to the Sun and migrated inward and then back outward in what is sometimes called the Grand Tack scenario. Saturn migrated alongside Jupiter. Uranus and Neptune, in some scenarios, formed closer to the Sun than they are today and were slowly pushed outward by gravitational interactions with the remaining disk material. The orbital architecture of the outer solar system we see today is the end result of this migration, not the starting state. During this period of giant planet migration, the inner solar system was a chaotic mess. There were not just 4 terrestrial planets in the early solar system. There were probably many more. There were dozens, possibly hundreds, of Mars-sized and Mercury-sized protoplanets jostling for orbital stability inside what is now the orbit of Mars. Most of them were destroyed. Some collided with each other in events the textbook would describe as planetary collisions, which is technically accurate but radically understates the scale. The collision that formed our moon, the so-called Theia impact, was an event of staggering violence in which a Mars-sized protoplanet slammed into the proto-Earth at orbital velocity and ejected enough material into space to coalesce into our natural satellite. Other early protoplanets were simply scattered out of the solar system entirely by close gravitational encounters with the migrating giant planets. This is the scenario in which Planet Y's lost sibling story takes place. Picture a fully formed rocky terrestrial protoplanet, somewhere between the size of Mercury and the size of Earth, originally orbiting in the inner part of the solar system. Picture this protoplanet having a close encounter with the young Jupiter or the young Saturn during the era of giant planet migration. The gravitational slingshot from such an encounter would not necessarily destroy the smaller body. It would simply throw it, hard, fast, in an unpredictable direction. Some such bodies would have been thrown out of the solar system entirely, leaving them as free-floating rogue planets in interstellar space. Some would have remained gravitationally bound to the Sun, but on enormously stretched, distant, slow orbits in the cold outer regions where they would be largely unobservable from Earth. If Planet Y is a lost sibling, that is its origin story. It would have been born in the warm inner solar system, perhaps in the same general orbital neighbourhood as Earth, Venus and Mars. It might once have had liquid water on its surface, or even an atmosphere capable of supporting some primitive forms of chemistry. Its formation environment would have been Earth-like in many ways. And then, in some dramatic encounter with a migrating Jupiter or Saturn, it was kicked out. It was banished. Its original orbit was torn apart and replaced with a trajectory that flung it into the freezing dark outer reaches of the solar system, where it has remained ever since. It is, in this scenario, a frozen mirror of Earth, a world that might have been displaced into permanent exile. There is something genuinely poetic about this idea, but also something deeply troubling, because it implies that the orderly arrangement of our current solar system, the 4 neat rocky planets in the inner disk and the 4 gas giants out beyond, is not the original arrangement. It is the arrangement that survived. There were other planets, and they were thrown away. The fact that we might be able to find one of them, hiding in the dark out at 150 AU, would be evidence that the early solar system was even more chaotic than current dynamical models suggest. It would mean the migration of Jupiter and Saturn was violent enough to scatter not just isolated icy planetesimals but fully assembled rocky worlds, and it would force us to re-examine our estimates of how often this kind of event happens around other stars and how stable any given solar system actually is on long timescales. But the lost sibling scenario is not the only possibility. There is another origin story for Planet Y that is, in its own way, even more strange. Because if Planet Y is not a lost sibling of Earth, it might not be a sibling at all. It might not have been born here. It might have come from somewhere else. Part 11. The Captured Rogue Scenario. The alternative origin story for Planet Y starts with a category of object that, until very recently, was largely a theoretical curiosity. The category is called the rogue planet. A rogue planet is exactly what it sounds like. It is a planetary mass body that is not gravitationally bound to any star. It wanders through interstellar space alone, untethered, carrying no light source of its own, drifting through the dark gaps between solar systems on whatever trajectory it happened to acquire when it was originally ejected from wherever it was born. For a long time, rogue planets were considered a marginal phenomenon. They were thought to be rare. Astronomers assumed that most planets once formed in a stable solar system would stay put. But over the past 2 decades, a series of microlensing surveys, in particular the Ogle survey based in Poland, have begun to reveal that rogue planets are not rare. They may in fact be one of the most common types of object in our galaxy. There may be more free-floating rogue planets in the Milky Way than there are stars. The numbers are still uncertain, but the lower bounds are themselves staggering. Recent estimates suggest that there could be tens of billions, possibly hundreds of billions, of rogue planets adrift in our galaxy, each one an entire world that, as far as we can tell, never managed to settle into a stable orbit around a host star, or was ejected from its original solar system by some violent gravitational event. These rogue planets are, by the very definition of the category, almost impossible to detect directly. They emit no light, they reflect no significant amount of stellar radiation, and they pass through interstellar space on trajectories that bring them close to other objects only on incredibly rare occasions. We can detect them, when we detect them at all, only through gravitational microlensing, which is the brief brightening of a background star as a foreground object passes in front of it and acts as a gravitational lens. Microlensing surveys have allowed us to estimate the population of rogue planets statistically, but they do not give us individual maps of where any specific rogue is at any given moment. Most of them are, in the most literal sense, invisible to us. Now here is the implication for Planet Y. If rogue planets are as abundant in the galaxy as recent surveys suggest, then the probability that one or more of them has, over the 4.5 billion years of our solar system's history, drifted close enough to the Sun to be gravitationally captured into a bound orbit is not negligible. Capture of a free-floating planetary body by a star is a difficult dynamical problem. It generally requires a coincidence of low relative velocity, the right approach geometry, and often the participation of a third body that can absorb some of the excess kinetic energy and let the captured object settle into a bound state. None of these conditions are easy to satisfy, but all of them are possible, and given enough time, given the enormous integrated probability of close approaches over billions of years, the expected number of capture events for any individual star is not zero. If Planet Y is a captured rogue, that would be its origin story. It would have formed billions of years ago around a different star. It would have been ejected from that original solar system, probably during some violent dynamical event involving migrating gas giants, much like the lost sibling scenario but happening in someone else's solar system rather than our own. It would have spent some unknown amount of time, possibly hundreds of millions of years, drifting alone through the interstellar dark, and then, in some long-forgotten encounter, it would have approached our young sun on a trajectory low and slow enough to be captured into a bound orbit. From that point on, it has been part of our solar system, but it would not be in any genealogical sense related to the rest of the planets here. It would be a foundling, a stranger taken in. If this is what happened, the implications are even more profound than the lost sibling scenario. It would mean that we have, embedded in our own solar system, a sample of a planet that formed somewhere else in the galaxy. A planet that carries, in its bulk composition, in its isotopic ratios, in its mineral inventory, the fingerprint of a different protoplanetary disk around a different host star at a different time in galactic history. We would be able to study, for the first time, an exoplanet that we did not have to view across light years of distance through the diffraction-limited blur of a telescope. We could in principle send a spacecraft to it. We could measure its surface composition directly. We could compare it, atom for atom, to the planets that formed in our own solar system, and learn something fundamental about whether the chemistry of planetary formation is universal, or whether it depends sensitively on local conditions. The captured rogue scenario would also tell us something important about the broader population of rogue planets in the galaxy. If we can find one captured specimen in our own solar system, we can begin to characterize what these objects are actually like, what they are made of, how they age, how they evolve under the harsh conditions of interstellar space. We have already begun to do this, in a limited way, through the recent identification of interstellar comets like Oumuamua in 2017 and Borisov in 2019. But those were small bodies, just transient visitors that passed through and continued on their way. A captured rogue planet would be a permanent resident. We would have all the time in the world to study it once we found it. Both the lost sibling and captured rogue origin stories are, in principle, distinguishable through detailed observation. A lost sibling born in the inner solar system and scattered outward would carry isotopic signatures that match the rest of the rocky planets here. Its mineral inventory would look like the inventory of Earth, Venus, Mars and Mercury, perhaps with some modifications from billions of years of cold storage in the outer solar system. A captured rogue, by contrast, would carry isotopic signatures that look subtly different. Its bulk chemistry would be a fingerprint of a different protoplanetary disk, with potentially different ratios of carbon and oxygen, and the various trace elements that vary from one stellar system to another. Once we found Planet Y, in other words, we would be able to interrogate it for the answer to the question of where it came from. The body itself would tell us its own origin story, in a language written in atoms, but all of this depends on actually finding it. And the question of why we have not yet found Planet Y, despite decades of dedicated outer solar system surveys, is the next layer of this story. Because if Planet Y is a Mercury to Earth mass body sitting 150 AU from the Sun, you might reasonably ask why we have not just pointed a telescope at it and taken its picture. The answer is that space is much, much larger and much, much darker than most people intuitively realize. Part 12. Why we have not found it yet. There is a tendency, when you talk about the size of the solar system, for the numbers to lose their meaning. People hear that one astronomical unit is 93 million miles, and they nod and they say, sure, big number. People hear that the candidate Planet Y orbits at 150 astronomical units, and they think, sure, that is pretty far. But the human mind is not built to viscerally appreciate the kind of scales we're dealing with here. Let me try to give you some physical intuition for what 150 AU actually means, so you understand why a hidden rocky planet at that distance is so genuinely difficult to see. Imagine that the orbit of the Earth, 93 million miles in radius, has been shrunk down to the size of a basketball. Just a basketball, sitting in the middle of a basketball court. The Sun, in this scaled-down model, would sit at the centre of the basketball, and the Earth would orbit on the outer rim, at a distance from the Sun of about 4.5 inches. In the same scaled model, where would Pluto be? Pluto orbits at about 30 AU, so it would be 140 inches from the centre, or about 11.5 feet from the basketball. In the same model, where would the inner edge of the Planet Y candidate region be at 80 AU? It would be 370 inches out, or just over 30 feet from the centre of the basketball. The outer edge at 200 AU would be more than 75 feet away, and Planet 9, at the inner edge of its candidate region, would be 150 feet away. The outer edge would be 300 feet away, more than the length of an entire basketball court. That is the geometry of the outer solar system. We are looking, with our current generation of telescopes, for a small dim object somewhere between 30 and 75 feet away from a basketball, in a model where the entire inner solar system fits inside the basketball itself. That object reflects almost no light. It moves so slowly across the sky that you cannot detect its motion in any single image. It has an orbital period of nearly 2,000 years, which means that across the entirety of human civilization since the beginning of recorded history, it has completed only about 3 orbits. To find it, you cannot just glance at the sky. You have to take painstakingly precise images of the same patches of sky over years, looking for the one tiny pixel that has shifted position by a fraction of an arcsecond between observations. And the searches are not random. The searches have to be targeted to the most likely regions of sky based on the predicted orbital parameters. But the predictions themselves carry uncertainty. The Princeton simulations narrow down the candidate orbital distance and inclination, but they do not pinpoint Planet Y's current location on that orbit. Planet Y could be anywhere on its 1800-year orbit at the moment. It could be near Aphelion, the farthest point from the Sun, where it would be at its faintest and most spread out across our line of sight. It could be near perihelion, the closest point, where it would be brighter but moving faster across the sky. We do not know. The math gives us the orbit. The math does not tell us the phase. Add to that the constraint that surveys of the outer solar system are bandwidth limited. A telescope can only image so much sky per night. A survey like the ones being conducted with current ground-based instruments takes years to thoroughly cover the entire sky, and even then it has to take multiple images of the same region over time to detect motion. Given the slow, apparent motion of any body at 150 AU, you might have to wait months or even years between observations of the same patch to detect the planet's drift. And during all that time, the planet itself is barely moving, just a few arcseconds per year against the background of stars, which is at the very edge of what current detectors can resolve. Here is the punchline. The technology to do this kind of search, to systematically and methodically scan the entire sky for slow-moving objects faint enough to potentially be Planet Y, is just now becoming available. Earlier generations of telescopes could have detected Planet Y if it happened to drift through their field of view at the right time, but they could not perform a comprehensive search. They lacked the wide-field imaging, the cadence, the data processing pipelines, and the deep sensitivity required. Dedicated outer solar system surveys over the past 2 decades have ruled out Planet Y across some patches of sky, but vast regions of the celestial sphere remain effectively unsearched at the relevant sensitivity level. If Planet Y is sitting in one of those unsearched regions right now, we simply have not had the chance to find it yet. That is changing. Right now, in 2026, the instrument that finally gives humanity the ability to systematically search the entire southern sky for objects like Planet Y has just opened its eyes. It sits high in the Chilean Andes, on a ridge called Cerro Pachon, and it is by any reasonable measure the most powerful astronomical survey instrument ever built by human beings. It is called the Vera C. Rubin Observatory, and the survey it is about to spend the next decade conducting was, in a sense, designed for exactly this moment. Let me tell you about it. Part 13. The Vera Rubin Observatory and the Eyes That Just Opened. The Vera C. Rubin Observatory sits at an elevation of about 8,700 feet on a remote ridge in the Chilean Andes, in one of the driest and clearest atmospheres on Earth. The site, Cerro Pachon, was chosen after years of careful study of the world's possible observatory locations. It offers more than 300 clear nights per year, almost no light pollution, low atmospheric turbulence, and easy logistical access to the city of La Serena on the Chilean coast. It is, in short, one of the best places on the planet from which to observe the night sky. The observatory is named after Vera Rubin, the American astronomer who, in the 1970s and 1980s, accumulated the observational evidence that established the existence of dark matter as a real component of the universe. Rubin spent her career meticulously measuring the rotation curves of spiral galaxies and showed, beyond reasonable doubt, that the visible matter in those galaxies could not account for their observed gravitational behavior. Something invisible, something with mass but no light, had to be present in vast quantities. The discovery of dark matter was Rubin's intellectual legacy, and the observatory bearing her name is in many ways an instrument designed to extend that tradition. It is built to measure, to count, to catalogue, and to find what is hiding in the dark. Construction of the observatory began in 2015, after more than a decade of planning. The instrument achieved first light, the moment when its main camera first captured photons from the sky, in June of 2025. It entered full operations in the latter part of 2025, and its flagship survey, the Legacy Survey of Space and Time, abbreviated as LSST, began in early 2026. The survey is designed to run for 10 years. Over the course of that decade, it will image the entire visible southern sky every few nights. It will return to the same patches of sky, again and again, building up a cumulative record of how the sky changes over time. Stars that vary in brightness will be tracked. Asteroids will be discovered and orbital fitted. Supernovae will be caught early. And, critically for our story, slow-moving outer solar system objects will, over the course of the survey, reveal themselves through their drift across the celestial sphere. The technical specifications of the Rubin Observatory are extraordinary. The primary mirror is 8.5 meters across, making it one of the largest survey telescopes ever built. The mirror is what is known as an off-axis design, with a tertiary mirror integrated into the central region, allowing for a wide field of view that conventional telescopes cannot match. The imaging sensor is the largest digital camera ever built for astronomy. It has 3,200 megapixels. To put that number in perspective, the camera in your smartphone has somewhere around 40 to 50 megapixels at the high end. The Rubin camera has more than 60 times that resolution, and the individual pixels are designed to be sensitive to extremely faint light levels, with a wide dynamic range that lets the camera capture both bright stars and faint distant objects in the same exposure. Each night of operation, the Rubin Observatory generates approximately 20 terabytes of imaging data. That is a staggering volume of information. Over the course of the 10-year LSST survey, the total data catalogue is expected to exceed 60 petabytes, comprising tens of trillions of individual measurements of objects across the sky. The data processing pipeline alone is a feat of computational engineering, automatically detecting and cataloguing variations in brightness, position, and other observable properties for hundreds of millions of objects per night. The catalogue of solar system bodies that Rubin will produce by the end of its survey is expected to dwarf the catalogue produced by every previous survey combined. For the search for Planet Y, this is exactly the right instrument at exactly the right time. The Rubin Observatory's combination of wide field of view, deep sensitivity, and regular cadence is uniquely suited to the detection of slow-moving outer solar system objects. A body like Planet Y, drifting across the sky at a fraction of an arc-second per night, would reveal itself in the Rubin data over the course of weeks or months as a single pixel that systematically changes position from one image to the next. The data processing pipeline is designed to automatically flag exactly this kind of slow-motion candidate for follow-up analysis. If Planet Y exists in the southern sky during the 10 years of the LSST survey, and if its surface reflectivity is anywhere within the plausible range, the Rubin Observatory should detect it. The detection threshold for Rubin is approximately magnitude 24 to 25 in red light, depending on the cadence of observations and the specifics of the source. A Mercury-to-Earth mass body at 150 AU, with a low albedo characteristic of an outer solar system surface, sits in the difficult middle of that detection envelope. If Planet Y is on the larger and brighter end of the candidate range, closer to Earth mass with a slightly higher albedo than the typical Kuiper Belt object, Rubin should pick it up readily. If it is on the smaller and darker end, closer to Mercury mass with the lowest plausible reflectivity, the detection becomes harder, but not impossible. The survey is sensitive enough to give us a real shot at finding it within the first several years of operations. There is also an important secondary point. Even if Rubin does not directly detect Planet Y, the survey will dramatically expand the catalogue of trans-Neptunian objects whose orbits define the warp. With 10 years of additional data on tens of thousands of new outer solar system bodies, the inferential argument for or against Planet Y will become much sharper. If the warp signature persists and strengthens as the catalogue grows, the case for a discrete perturber will become harder to dismiss. If the warp weakens or disappears as new objects are added, and observational selection effects are better characterized, the case for Planet Y will collapse on its own without anyone having to find anything. Either way, the next decade is going to settle the question. This is the moment we have been building toward for almost 2 centuries. Leverrier's method, invented in 1846, perfected in 2016 by Brown and Batygin, and now applied to a different anomaly by the Princeton team in 2026, is about to meet the most powerful sky survey ever built. The inferential argument is on the table, the instrument is online, the test is about to begin. But before we close, I have to deal with the cultural neighbours of this story. Because whenever you tell a general audience that there might be a hidden planet out beyond Neptune, the conversation inevitably gets pulled toward a different set of ideas that have, fairly or not, occupied the same conceptual space for a long time. I am talking, of course, about Nibiru, about Planet X, about Nemesis, about the half-century of fringe theories that have predicted hidden worlds in the outer solar system for reasons that have nothing to do with the careful inferential science the Princeton team is doing. I want to be clear about why Planet Y is not any of these things, because the distinction matters. Part 14, Nibiru, Nemesis, and the fringe theories Planet Y is not. Whenever a serious scientific claim is made about a hidden planet in the outer solar system, the cultural baggage of half a century of fringe theory gets dragged into the conversation. So let me address the cultural neighbours directly, because the audience will inevitably be reaching for them, and the science we have just been discussing deserves to be cleanly separated from the catastrophist legends that share its general topography. The most famous of the fringe theories is Nibiru. Nibiru, also known under various aliases as Planet X, Wormwood, the Destroyer, and various other apocalyptic names, originates with the writings of Zecharia Sitchin in the 1970s. Sitchin claimed to have decoded ancient Sumerian texts as describing a hidden 10th planet on a 3,600-year elliptical orbit, periodically returning to the inner solar system and triggering catastrophic events on Earth. Nibiru has been revived and repredicted dozens of times over the past 5 decades, most prominently during the 2012 Mayan calendar doomsday cycle, and it has consistently failed to materialize. Nibiru is incompatible with basic celestial mechanics. A planet on a 3,600-year orbit returning to the inner solar system would have been observable by every observatory on Earth for years before any predicted arrival, and modern infrared sky surveys have systematically ruled it out at every relevant distance. It is not real. It has never been real. It is, in the strict scientific sense, a non-existent entity that has been kept alive by the willingness of various authors to keep predicting its arrival. The Nemesis hypothesis is a separate idea, originally proposed by physicist Richard Muller in 1984 as a serious scientific conjecture. Nemesis was a hypothesized brown dwarf companion to the Sun on a long elliptical orbit. The idea was that periodic perturbation of the Oort cloud by Nemesis could explain apparent cycles in the mass extinction record on Earth. Nemesis, unlike Nibiru, was a serious scientific hypothesis at the time it was raised. It was the subject of legitimate research papers and sky surveys aimed at testing its predictions. But Nemesis has since been ruled out by infrared sky surveys, most definitively the WISE mission, which would have detected any brown dwarf mass body within the relevant distance. There is no Nemesis. The scientific community has accepted this and moved on. Planet Y is none of these things. Planet Y is not Nibiru. Planet Y is not Nemesis. Planet Y is, in scope and methodology, much closer to the discovery of Neptune in 1846 than to any of the catastrophist legends that have circled the idea of a hidden outer planet. The Princeton claim is a quantitative argument from gravitational perturbation, the same method that delivered Neptune, the same method Brown and Batygin used in 2016 to argue for Planet 9. It belongs to the legitimate scientific tradition of inferring unseen mass from the behavior of seen bodies. It carries no apocalyptic associations. It has no predicted approach to Earth. It is not on a periodic inner solar system encounter trajectory. It is, as far as the Princeton simulations can tell, a stable, distant, frozen world quietly orbiting in its own warp at 150 AU, exerting gravitational influence on its icy neighbours but having no measurable effect on anything inside the orbit of Neptune. There is a more interesting cultural question worth raising, though. Why is it that the model of the solar system we all grew up with, the orderly arrangement of Sun and Mercury and Venus and Earth and Mars and Jupiter and Saturn and Uranus and Neptune and historically Pluto, keeps getting destabilized by new discoveries every few decades? The Pluto demotion happened in 2006. The Planet 9 hypothesis arrived in 2016. The Planet Y hypothesis is now being put forward in 2026. The pattern suggests that the official planet count is far less stable than we have been treating it. The honest answer is probably that we have always treated the solar system as a closed, well-mapped system, when in fact we have only ever explored a tiny fraction of its volume. Beyond Neptune, the solar system stretches outward through the Kuiper belt, through the scattered disk, through the inner Oort cloud, and out to a heliopause beyond which our instruments have barely begun to probe. There is a very large amount of room out there for the unknown to hide. The uncomfortable truth is that the discovery of a real additional planet would not represent a violation of the laws of nature so much as a long overdue update to a map that has always been more incomplete than we admitted. We have known, in some abstract intellectual sense, that the outer solar system might harbour surprises. We just have not had the tools to look for them properly. Now we do. And the question of what the tools will turn up is the question of the next 10 years. Part 15. What confirmation would mean and the null we cannot forget. Let us imagine for a moment that the search succeeds. Let us imagine that within the next several years, the Vera Rubin Observatory's data pipeline flags a single faint pixel that systematically shifts position from one image to the next at the slow rate consistent with a body at 150 astronomical units. Let us imagine that astronomers around the world point follow-up telescopes at the candidate location, refine the orbital parameters, and confirm that the object is real. Let us imagine that within 5 years, 10 years at the outside, we have a publicly announced 9th planet of our solar system. What would that mean, exactly? What would change? The first thing that would change is our understanding of how planets form. If planet Y is real and is approximately Earth mass, then our current model of planet formation is missing something fundamental. The standard model says that the protoplanetary disk surrounding a young star simply does not have enough material at 100 AU to coalesce into a rocky terrestrial world of that magnitude. The disk is too thin out there. The temperatures are too low to drive efficient grain growth. The dynamical timescales for assembly are too long. By every account in the current textbooks, a Mercury to Earth mass body should not be able to form in situ at 150 AU. So if it is there, it had to get there some other way. Either the lost sibling scenario, in which it formed close in and was scattered, or the captured rogue scenario, in which it formed somewhere else entirely. Either way, our model expands. The second thing that would change is our intuition for how often this kind of event happens elsewhere in the galaxy. If there is one planet Y around our Sun, the implication is that every star in the galaxy should be producing or capturing similar bodies at some non-trivial rate. The galaxy may, in fact, be full of hidden frozen worlds in the outskirts of solar systems, invisible to all our current detection methods, quietly orbiting in the cold dark beyond their host stars. We would have to start asking how common the captured rogue scenario actually is. We would have to recalculate our estimates of the total planet population in the Milky Way. We would have to add a category, the captured exoplanet, to the inventory of known planet types. The third thing that would change is more philosophical. The discovery of planet Y would mean, very concretely, that the solar system we live in has been hiding a major secret in plain sight for the entire history of human civilization. Every generation of astronomers, going back to Galileo, going back to the ancient Babylonians, has assumed they had a complete inventory of the worlds around our Sun. They have all been wrong. We have been wrong. The universe, even at its most local, is genuinely larger and stranger than we have allowed ourselves to acknowledge. There is something in that fact that I find both humbling and exhilarating. The universe is not exhausted. There is still discovery to be done, and some of it is not in distant galaxies or at the edge of the observable universe. Some of it is right next door, drifting in the dark, waiting for someone to actually look. But I have to balance this excitement with the null hypothesis, because there is a real possibility that the search will turn up nothing. The Vera Rubin Observatory could spend the next 10 years methodically scanning the southern sky, characterizing tens of thousands of new trans-Neptunian objects, sharpening the data on the orbital warp, and find no planet at all. That outcome is not failure. That outcome is also a discovery, and a deeply important one. If the warp is real but no perturbing body is found, then the field will have to systematically eliminate the planet hypothesis and turn to the alternatives. Was the warp produced by a long-past stellar flyby that no longer needs an active source? Is it being maintained by a diffuse population of small bodies we have not yet detected? Is there something subtle about the gravitational physics of the outer solar system that we are still not modelling correctly? These are also valuable questions. A clean null result on planet Y would force us to investigate them in ways we currently are not. It would tell us that the simple discrete perturber explanation is wrong, and that the truth about the outer solar system is more complicated than the elegant Leverrier-style story we have been telling ourselves. That kind of negative result is, in a certain sense, even more scientifically valuable than confirmation, because it pushes us into territory we did not expect to need to explore. The Planet 9 hunt, after all, has already been informative even without a confirmed detection. The decade of searching has generated huge amounts of new data on outer solar system bodies. It has refined our models of the Kuiper Belt. It has produced a vastly improved understanding of how observational selection effects shape our catalogues. The hunt for Planet Y, whether it succeeds or fails, will produce similar dividends. We will know more. We will understand more. We will have a sharper picture of what is out there in the cold dark. So here is where we stand at this moment in the spring of 2026. A team at Princeton has identified a 15-degree warp in a population of outer solar system bodies, run the simulations, and concluded that the cleanest explanation is the existence of a hidden rocky planet between 80 and 200 astronomical units from the Sun. The candidate planet would be Mercury to Earth in mass, frozen, dark, silent, and either a lost sibling of Earth scattered into exile by a young Jupiter, or a captured rogue planet bound to our Sun in some long-forgotten encounter from the deep past. The Vera Rubin Observatory in the Chilean Andes has just opened its eyes. Over the next 10 years, it will systematically search the southern sky for exactly this kind of slow-moving distant object. By the time the survey ends, we should know. I want to leave you with one final thought, because I think it captures the strangest part of this entire story. We are at this point in human history because of the patient accumulation of thousands of orbital measurements of icy bodies in the outer solar system, performed over decades by hundreds of astronomers around the world, none of whom knew they were collecting evidence for a hidden planet at the time. Every individual measurement was just a data point, every individual orbit was just a number, but in aggregate the data revealed a pattern. The pattern revealed a fingerprint. The fingerprint revealed, possibly, a world. This is how science actually works, not in single dramatic moments of discovery, but in the slow accumulation of evidence over generations, until eventually the evidence becomes strong enough to demand an answer. The answer to the warp may turn out to be Planet Y. It may turn out to be something else entirely. Either way, the question itself, the fact that we're even able to formulate it with this much specificity at this moment in history, is a quiet triumph of method and patience. We're about to find out what is hiding out there, and whatever it turns out to be, the act of looking is going to teach us something about a part of our own solar system we have been ignoring for too long. The map of the worlds around our Sun has always been more incomplete than the textbooks pretended. The next decade may finally start to fill in the missing piece, or it may show us that the missing piece is not a piece at all, but something stranger, something we have not yet learned how to imagine. Either way, the dark out there is about to get a little less dark, and the old assumption that we knew the basic count, that there were 8 planets and 1 demoted dwarf in a long tail of icy debris and that was the whole story, is about to be tested in a way it has never been tested before. The instrument is online, the data is starting to flow, the hidden world, if it is there, will not stay hidden much longer. We have spent 400 years building tools to look at the sky. We're about to find out whether one of them, finally, can find what we have been missing the whole time. And when the answer comes back, whichever way it comes, we will have learned something fundamental about the place we live and about how much of it we have not yet truly seen. The dark beyond Neptune is the last great unmapped frontier of our own solar system, and it is about to give up at least one of its secrets. The only question is which one and how soon.